Okay. Work done means the sign of work will be positive because the system is doing the work, so it's expending the energy. Then you asked a question about number 27 from end of chapter 5. And the problem, it gives you a balanced equation. And it says that equation releases 879 kilojoules of heat per mole. Well, that means per mole is written. So it means per 2 moles of zinc sulfide. And I'm saying that because that's what the question's asking about the zinc sulfide. For example, it would be 879 kilojoules of heat for 3 moles of oxygen. Okay, but this is the one we've got to worry about because that's what it's asking about. The question asks, calculate that to kilojoules per gram. Well, see, you have kilojoules per mole. All you need to do is a mole to gram conversion. A mole of zinc sulfide is how many grams of zinc sulfide, and that's going to be using the molar mass of zinc sulfide to get that. Then your other question was on number 37. Okay. So on number 37, you have gold and you have iron. Okay? And so it's all about calorimetry. So it's all based around Q equals MS delta T. So, 37. Gold is 10 grams. That's the M. S. And then delta T is final and initial. So, the initial temperature of the gold is 18 degrees Celsius. It's placed on a flat sheet of iron weighing 20 grams at a temperature of 55.6 degrees Celsius. And it says, what is the final temperature of the combined metals? So see, they're both going to reach the same temperature, X. And X is identical for both of them. And it says, hint, the heat gained by the gold, so the Q of the gold that it gains, must be equal to the heat lost by the iron. And then the specific heats are given in table 5.2, so we're going to look that up. Oops. Specific heat of gold is 0.129 joules per gram times degrees Celsius. And for iron is 0.444 joules per gram times degrees Celsius. So Q equals MS delta T for the gold is equal to the negative MS delta T for the iron. So how we're going to set that up is we're going to say the MS delta T for gold is equal to the negative MS delta T for iron. So then I'm going to take numbers from this table and plug those in here. I'm going to leave out units because I'm going to run out of room and it's going to get really confusing over here. But if you had plenty of room, you could, of course, show the units. So gold, M is 10, S is 0.129, and delta T is X minus 18. Iron, don't lose that negative. M is 20, S is 0.444, and delta T is X, see I'm running out of room, minus 55.6. And from this point, it's just algebra. 10 times 0.129 times X, and then, which is 1.29X, right? Minus 10 times 18. See, and you just do the algebra and solve for X. Okay, let me pause this because that's your chapter 5 questions. Okay, first chapter 7 problem, you had a question on number 47. And it says, 2 atoms have the electron configuration 1s2, 2s2, 2p6, and then The other one is 1s2, 2s2, 2p6, 3s1. Okay, so let's think about what this looks like in terms of an electron orbital diagram. Oops. Okay, the other one looks like this, except it has a 3s1 at the top. Okay, then it says the first ionization energy. So that's removal of the outermost electron. So for the one on the left, we're talking about taking this electron away. For the one on the right, we're talking about taking this electron away. This one on the right, it's not going to be hard to take that electron away, because look, it's right there by itself. It's really a valence electron. So it's not going to take a lot of energy. But the one on the left, that's going to take a lot of energy to take that electron away. See, it's real stable when they're all paired up like that. So that's why the one on the right would be the lower energy, the 496 kilojoules, and the one on the left would be the 2000 kilojoules. And then did I do the wrong one? No, number 85. Okay, in order of increasing ionization energy is removing an electron. Okay. The more positive it is, it's already lost the electrons it wants to lose. That's why it takes more energy. And see, the negative ones have actually gained electrons. So removing electrons could take them back to their neutral state. And like for magnesium with a +2 charge, it's going to take the most energy because it's already lost its 2, and now you're entering into its noble gas. Like if you look, I actually am doing this. I don't have a periodic table right in front of me. But magnesium's, the end of its electron configuration is what? 3s2? And so when you take these electrons away, you go to magnesium's noble gas core. Does that make sense? I hope so.